This is the first page of the Students T-Test mini unit. It's only 2 problem set pages long. This is from the new curriculum, so it's from the new textbook, page 407 to 410. I included some of the book here to talk about how it works and when you apply it. This is a super useful test that even if you don't go into some math-related field, you might have time you can use it. I know that teachers use it a lot. Over the years, I've had teachers ask me to help them use it for research. I've also helped a lot of students use it in science fair because it's very useful in science fair, but it's not taught in any class at EAC until now. Okay? So here's the problem that we start with looking at. Maisie noticed that the sun shines more on one side of her garden than on the other. She wanted to know whether this had any effect on the height of the tulips on either side of the garden. She measured 20 tulips from each side of the garden in the data shown in the table. One of the most easiest things to apply in the IA is chi-squared. The second most easiest thing to apply might be this, okay? This or linear regression, okay? So if we look at the data that Maisie collected, she has the right side of the garden tulips and she has the left side of the garden tulips here. I made an abbreviated list here in the book. It goes a lot further, but I just put the first 4 lengths on each of these, okay? Let's talk about what this has to do with normal distribution, because sometimes we're going to do this at the end of the normal distribution unit. If you take all these tulip lengths, as we learned in normal distribution, typically these tulip lengths, like many other complex one-variable processes, are going to be arranged in a normal distribution. If you have 2 normal distributions that are measuring a similar quantity, then the way you would compare the 2 populations is you would use T-test. Okay, so each one of these is a normal distribution. You want to know, are these normal distributions on top of each other? Are they to the left or to the right of each other? Imagine you have data and you have maybe like the tulips on the right side, the tulips on the left side, and you're wondering if one gets more sun and they're longer than the other. Maybe you look at heights of children in different countries or something. You can imagine that they would be normal distributions arranged like this, right? By the way, they call it Students T-Test. Students T-Test. The reason why it's called Students T-Test and the reason why the S is capitalized is because the inventor, for some reason, didn't want to take credit for it, and he used a pen name Student to write the paper. I don't exactly know why, but he did. It's kind of confusing, right? Why is someone's name Student? But anyway, his real name was William Gossett, and it turns out he worked at the Guinness Brewing Company, which some of you may know. It still exists today and still continues to be very famous, especially among young people. And the job of William Gossett at Guinness was statistical quality, and he studied the quality of the beer. So you can imagine that maybe that would have been a really nice job. Imagine if you learn to use T-test well, maybe someday you could be a beer quality tester. Okay, the T-test is used for 2 data sets that are measuring the same thing, like the tulips above, and only applies to normally distributed data. Okay, so that pretty much applies to everything, as we remember. One variable data typically is normally distributed, right, as long as it's complex enough. There is a formula that is used to calculate it, but you won't need it, as your GDC will do the work for you. Okay, the null hypothesis is that 2 means x1 bar and x2 bar are equal. Okay, so what we're usually trying to do is trying to figure out if the 2 populations have the same mean, if they're centered at the same place. Your data, if you do the mean of this and you do the mean of this, you're not going to get the same mean. They might be close, but you know, just because they're off by 1.2 centimeters doesn't mean that if you didn't have enough samples that you would eventually have the same mean, right? So the T-test is used with a smaller population, you can determine if in reality they're close enough statistically that you could declare them the same. Okay, so the null hypothesis is the default, and it's that the two means are the same. Okay, so the only variation actually is the alternative hypothesis. The alternative hypothesis is when the null hypothesis is not true. So you might say, oh, well, the alternative hypothesis would be when x1 bar and x2 bar are not equal to each other. And that is true. That is one of the possible ways that it could not be true, right? The null hypothesis would not be true. But there's another way, which is what happens if you know for sure that one of the populations is either equal to or greater than the other. Those are the two possibilities. So there is no possibility that the first population is less than the other population. You know that it has to be bigger or equal to. In that case, it kind of simplifies things a little bit, because then you know that you only have two choices instead of three, and they call that a one-tailed test. So if you're going to do a one-tailed test, that means that the only possibility is that the two populations are on top of each other, or one is greater, but the other one can't be greater. Okay? All right. So let's see. So for a two-tailed test, the alternative hypothesis is that they are not equal to each other. So one might be less, one might be more. You're not figuring out which one is less or more. You are just figuring out that they're not equal to each other. Okay? And then for a one-tailed test, you're looking to see if one of the populations is bigger or smaller than the other. That's the alternative hypothesis. The opposite direction you are not allowing for. Okay? All right. Using your GDC, you will be able to find the t-statistic and the p-value. Does that sound familiar to chi-squared? Chi-squared, whenever we ran a chi-squared test, we had the chi-squared statistic and we had the p-value, right? We only looked at the p-value and compared that to the significance level. And here it's the same thing. There is a t-statistic. Maybe you might use it in science fair or other applications, but on the exam or in your IA, you're going to focus on the p-value for this class, and you're going to compare the p-value to the significance level. Okay, so the way you use it is you're going to put your data into the calculator. So I'm going to turn on the calculator, and I'm going to put those two lists in it. And of course, we're going to put the lists in our old familiar friend stat edit, and I'm going to put these two data columns in there, and I'm going to pause it while I'm doing that. There we go. The two columns are input into stat edit. Now, of course, we're going to do similar to chi-squared. We're going to do stat test, where we found chi-squared. And we are going to go down to, now be careful. It's not this t-test, which is only for one column of data. We have two columns of data, so we're always going to use two sample t-test, which is number 4. Okay? And then we're always going to put data, because we're not going to put in the mean and the standard deviation. We're going to put the entire data column. We're using list 1 and list 2 because those are the two leftmost ones. Frequency 1, frequency 2 should always be 1. And then now we need to say, okay, what is the alternative hypothesis? In this particular case, let's see, the null hypothesis that MAISL believes the right side tulips mean is mu1 is the same as the left side mean mu2. The alternative hypothesis, MAISL believes that the right side mean mu1 is not the same as left side mean mu2. So that means it would be this one here, not equal to mu2, right? If the alternative hypothesis is that MAISL believes that the first mean is less than mu2, that would be this alternative, right? Pooled, you will always put yes, and maybe the only time you wouldn't put yes is in your IA, and we can talk at the time of your IA about what this means. But basically what it means is that the two data columns are similar enough that you believe that each population has the same sigma, even if that small sample does not. If you had a larger sample, you believe that they would converge to the same sigma. And then I go down to calculate and hit enter, and then it gives me the t-value, which we don't use for the exam or for this class, and it gives me a p-value, degrees of freedom, etc., etc. We don't use the degrees of freedom in the test problems. The mean, if they ask you, you have them here, and you also have SX1, SX2, and SX pooled is a combination of these two. So this is like your sigma, and this is like your pooled sigma, which like uses all the data points, okay? And then of course you have 4 samples in the first and 4 samples in the second. You can actually use this test even if you have 2 populations that have a different number of data points, okay? So what does this 0.251 mean? This is the most important thing on this, and this is the one what you're going to use on the exam and on your IA. 0.251 is a number that it's the p-value, and you're going to compare it to the significance level. So the significance level in this case is either 1%, 5%, or 10%. Most commonly, 5% is used. In this particular case, we are going to compare it with 5%. So we put 0.05 to compare it with 0.251, the p-value. We find out that 0.251 is bigger. Remember, p-value is the opposite of the chi-squared statistic. If it's greater, we accept the null hypothesis. So when 0.251 is greater than 0.05, we accept the null hypothesis, or we don't reject the null hypothesis, which means that basically the 2 populations are the same. Okay, so even though the sun is shining more on one than the other, it didn't really affect the growth, is what it says. So you can kind of see how this might be used in a science fair, right? And that's it for the introductory page.